Okay. 1st go over the 11th module from the presentations. Actually, let's 10th, 11th, 12th, just to see what is left. So last week we discussed, we were doing this earth pressure theory. We did some questions on that. It's fine. And then in week 11 also we've got same earth pressure theory, some questions on earth pressure theory. And then the last topic is slope stability. Okay. There are some questions that I have on. Okay. There are some questions on retaining walls that we can go over, and after that we can discuss. Excuse me. Just a minute. After that we can discuss a bit of the theory for slope stability, if that is okay. Or would you like to discuss a theory on slope stability and then discuss the questions for retaining wall? Uh, would be better. You can mention in the chat, or you can uh, open your microphone, mention. Should we discuss the theory on slope stability first, or should we go for the questions on retaining wall first? Yes, Rayan. Slope stability theory. Okay, so fine. We will go over the theory first, and then in next lecture we will do some questions on slope stability. Today we will discuss the theory on slope stability and cover the questions. Okay. Okay. Uh, so basically, actually, let me I'll open it on my second display. Right now, my display is a little, um, it's not what I have usually. So I'll only be displaying the PPT file. Okay. Okay. So these are, just a minute, I have changed the settings a bit. Just working. Just a minute, please. Okay, that's better. So because this is soil mechanics one, since this is the 11th week and we have one more week, we can discuss what all we have studied, and we can discuss what are the important topics that we study, what are the core topics of geotechnical engineering. So, starting from the beginning, we started with character classification. We talked about index properties, which actually comes in classification. We talked about your grain sized distribution curve, and we talked about engineering properties, So these are the initial beginning things that you study soil. Then you talk about some of the properties. We talked about compaction, we talked about consolidation, we talked about permeability and seepage. So all of these are phenomena. Still, we are talking about the state of the soil. Okay, you compact the soil, then you basically you want a particular void ratio. And consolidation is something that changes the state of the soil, as in it makes it. Um, this process takes place with time and it reduces the void ratio. Then again, we are talking about the property of soil permeability, how much water, like how the flow of water through the soil will be. Then we talked about the uh, stresses. First, we talked about stress at a point. We talked about stress below load. So these are, they tell you how load transfer takes place in soil. We've also covered earth pressure theory, which basically is lateral pressures. So until now, we are talking about the properties of the soil. Then we discussed the shear strength of soil. Given all these properties of the soil and the behavior, this is how the soil behaves, this is how the soil behaves, this is a property of soil, these are properties of soil. So you studied about the behavior of soil, how soil will behave in different scenarios, and then we talked about shear strength of soil. This is basically one of the most important topics for geotechnical engineers because our job is to assess, as engineers by name itself, we build stuff. So this has many sub branches. Our particular branch, geotechnical engineering, basically tells us that when we are building stuff over soil, how will soil behave? Will this soil bear the load of uh, the structure that has been built? So all the other topics of soil, the nutrition in soil, the nitrogen cycle, the agricultural part, that comes in soil science, that does not come in geotechnical engineering. Geotechnical engineering, we are concerned with building stuff over soil. So this can be there can be two scenarios. First is we have a flat land and we are building something over it. We use the shear strength of the soil inherent. Other scenario is we have a sloping land. Okay, here also we have two scenarios. One scenario is that we want to know if this slope itself is stable, be it natural or man-made. Because sometimes what we need to do is we need to create some slopes. Uh, Let me say, for example, you have a mountainous uh, track and you want to build a road somewhere here, and you need to do this kind of construction. So what you do is you excavate here. Now you want to know that will this hold or not, or you one natural slope, you have seen there are rock falls, there are landslides, and subsidences, liquefaction. So you study natural slopes and try to gauge if this slope is stable enough for what, such that if there is a population, if there is a construction somewhere here, they should not get damaged and there should not be a loss of lives. Other thing is man-made slope. For example, as I said, this is a vertical cut. You'll also study this in stability, like in retaining walls. We have sometimes we do these cuts along the face of the mountains, and we need to assess if these are stable. And so for cutting uh, in mountains, excavations. Okay, so now two scenarios are: first, you check stability of slope itself. The second scenario is if you are constructing something on this slope. So the second part comes under your geotechnical engineering too, when you study about the foundations. So what are the conditions you need to meet if you want to make a construction over a slope? In geotechnical engineering 1, we can discuss about the stability of the slopes. So basically, the introduction says the gravel and sand are referred to as granular soils and normally exhibit only frictional component of strength. Potential slip failure in a slope of granular material will be planar, and analysis of the slope is relatively simple. However, most soil exhibit cohesive and pure granular soils are fairly infrequent. Nevertheless, a study of granular soil is useful in introduction to the latter case. Okay, so there were two scenarios: flat land and sloping land. In sloping land, either we have man-made slope or we have a natural slope. Or in sloping grounds, we want to check the stability of the slope or the foundation. So, for starters, let's talk about finite and infinite slope. Finite, you know, something that is definite, and infinite is indefinite, as in um, finite slope is a slope for which you know the top and the bottom or the toe of the slope, you know the locations, or uh, not only know the locations, but the potential failure can happen in a slope in which this is not very far apart. But infinite slope, it's not like it is infinitely extending in space. That is not possible. But infinite slope, basically, what it generally means, it means that usually the slope is quite mild and it is long, such that the failure surface of the slope, the slip failure surface, is a bit shallow. It need not be shallow. It just, the proportions of the slope are such that, you see, if you have a circle but it is so large like the earth, it's so large that it seems flat to you. That is what infinite slopes actually depict. They depict a slip surface that is almost parallel to the uh, slope face. That is why we call it an infinite slope, because it does not have a particular head. It does have a head and toe, but the head and toe don't occur in the slip surface, and the slip surface for most part is kind of parallel to the, just a moment. Okay, so the slip surface is kind of parallel to the slope face, and this is the easiest method of checking out the slope stability. In this method, we just have parallel lines and our simple, whatever we have studied in physics. We used to study the inclined plane physics, kinematics. That is quite relevant here. Excuse me. In all the methods of slope stability, what we do is we idealize the slope angle, let us say beta. Okay, then we, for now, let us assume a slip surface, a body for failure, something like this. Let's assume for now. We are assuming that this body is going to fail. It's not supposed to be like this. Let's say it's like this. Because if it is that irregular, there will be interlocking effect and it will not fail. Let's say that the slip failure is something like this. Okay. So this, where does the stability of this slope come from? You know your inclined plane theory. Any object you place here will have some mass in the in this direction. Then if you divide it into the components, sorry, this was like this. So you will have, if this is beta, then this is beta, and this will be cos component, sine component, cos component, sine component, cos component, sine component, isn't it? So as you increase the slope, as the slope is increasing, this weight is the stabilizing force, isn't it? The normal force is the stabilizing force. The driving force is the, you see, this force is uh, making the body have a tendency to go down like this. While if this force was high, there would have been more adhesion towards this surface. The block would stick to the surface if this is more. And uh, so in slope stability, we use the same logic. What we do is we assume a slip failure, we take the weight of this failure wedge, and we factor it into your components. So then you basically check in all the methods that are there to calculate the safety. What you basically check is the, the difference or the relative values of the driving force, stabilizing force, and the driving force. Now, there are a few definitions of factor of safety. One of the definitions is that factor of safety is equivalent to your driving force, uh, no, stabilizing force over driving force. Okay, but all of the methods don't, some methods take into consideration only the frictional part of resistance. Some methods take into consideration cohesive part of resistance. So here basically what we are doing is in bulk we are taking the weight and then calculating the uh, driving and the uh, stabilizing forces. But some of the definitions, they want to take only the frictional component, so they take the tan uh, beta over tan phi, and sometimes it is c dash by c dash m. We can see that further. There are different methods of basically saying the same thing. The values will be different, but it does not mean that the slope is different. The slope will be same, but it will have different, because these are man-made concepts. Factor of safety, it's not something um, tangible, it's not something you can see or maybe even define. It's something we have calculated for our own purposes. So we can have different definitions of different things, um, and they may not because they don't physically mean anything. Whatever you define it by, is the definition. Okay. So okay. So here we talk about, this is the weight, this is the normal component, this is the tangential component. In most of the methods of slope stability, what we do is we make this vector triangle of these forces, the W, the N, and the tangential stress, and based on this we make our calculations, and you can see it here for example. So I will not go through the derivation of the factor of safety, but this is the most simple case, sorry, this is the simplest case in which you have a parallel slope. So you have the slope is like this, and this is quite long. So what you do is you take a unit section of the slope, analyze this unit section of the slope, and you apply the same logic to the entire slope. Okay. uh, so we have taken a wedge here that has parallel faces like this, and then we have calculated the resisting moment and the driving moment, the resisting force and the driving force. Normal reaction is W cos theta, the normal stress, normal effective stress, and then the tangential force, tangential shear stress, ultimate shear strength of soil, and hence factor of safety is given as ultimate shear strength. Okay, so basically what we have taken here is the driving force is the tangential component here, and the resisting force is the strength of the soil itself. One second. And for the strength of the soil, we need to know the normal component, because strength of the soil from Mohr's law we take as Mohr-Coulomb law we take as tau is equivalent to sigma tan phi, and sigma there is your normal stress, and your resisting force is strength of soil, the driving force is T here, resisting force is strength of the soil, which depends on normal component N. Okay, then Based on this, we get an expression. This was W sine beta, W cos beta. Then we have a W here, and this is beta. Then we have the resisting force, factor of safety is the resisting force over driving force. This can be written as W cos beta, which is N tan phi over W sine beta, which basically gives us simplest factor of safety tan phi over tan beta. If you consider that the slope now has some water, you see what will happen if the slope is partially or completely submerged or saturated. What will change is your W, and what will change is your effective stress. Here we are talking about the whole weight in the bottom, but at the top, when we talk about the factor of safety, we were taking as this is sigma tan phi over T. This is sigma tan phi W sine theta. Okay, but you know that this is the effective stress. Tau is equivalent to C plus sigma dash tan phi. So if you have a U, you will have factor of safety equals sigma minus U tan phi over W sine beta. This will be your W cos beta minus U over W sine beta tan phi. This will be this can be gamma, and these will be different. See, if the soil is simply saturated, it's just the bulk uh, uh, it's just the bulk weight of the soil if there is no water table. If there is a water table, then sigma dash will be based on gamma submerged. Okay, and in the bottom you will have gamma saturated only. We'll have gamma submerged minus, you don't need minus u now, tan phi. So you will have something like gamma submerged over gamma saturated, tan phi over tan beta for a submerged slope. Why? Because the resisting force will change, because you need to have the effective stress in the Mohr Coulomb formula. But the bottom force will take the whole of the weight. The bottom force is not based on the Mohr Coulomb formula. So you don't need to take the effective force. You will have to take the total stress there. Then next, ultimate shear strength of soil is sigma dash tan phi. Okay. So if there is flow, then based on the flow, what we studied in permeability, we talked about a seepage force. You have to take that into consideration in your vectors when we are taking the kinematic diagram of free body diagram of your slope stability. Basically, you have to take that force, that seepage force, into consideration. Then in week 12, so until now, this these equations, they're all based on granular soils, because you see we have not taken C anywhere. Everywhere we have taken sigma tan phi. But in C5 soils, what you have is you have a C component also. So you will have a more complicated, usually this kind of an infinite failure that is more common in granular soils. But in soils that have cohesion, you have a different kind of failure. You have a circular failure that can be a completely circular failure. The failure plane can be log normal, it can be circular, elliptical. Based on studies, usually we assume it to be a circular failure, and all the theories that have been given for slope stability of that kind of soils, basically what they do, one theory is in which you take the total stress theory, in which you take the whole failure wedge as a whole mass. Rest of the theories, what they do is they divide this whole wedge into slices. Okay, this is called the limit equilibrium approach. So what they do is they take one wedge. Basically, they have some theories on what will be the radius of the slip surface. Okay, once you know the radius of the slip surface and the center here. Once you know this slip surface, you divide your wedge into thin slices. Then you take the equilibrium of each slice. Basically, what you do is you make this long table kind of thing in which you enter the data for all the slices. For example, you have slices 1, 2, 3, 4. Then you take the center distance from the centroid, Z, the distance, let's say R, then the distance from the bottom, Z, then you take area, the weight of each slice. This gamma W, gamma into area, which is the weight, this will give you the weight of the wedge and moment, the driving moment. Okay, I'll tell you this. Let us say that this is on a trial and run basis. I'll assume a radius. I'll make these calculations. Okay, so when I make these calculations, this is what I will know. And the difference in different methods is basically how you are taking the equilibrium of the slices. For example, I think the Swedish circle theory does not take into consideration the inter-wedge, inter-slice forces, that is the forces that will be acting on these walls. But if you take that into consideration, you will end up with Bishop's theory. That's the only difference between these all these methods that have been given, is how you define this equilibrium. Let us go to the notes and check. So we can have a toe failure, or we can have a base failure, something like this. And as I said, what we need is we need the radius and we need the center. So this is the total stress theory that I was mentioning, in which you take the whole of the wedge, you take the whole of the wedge, the length of this failure plane, you know the length of an arc is r times theta. The length of this failure plane is r theta. If you assume C as if you assume C as this is the cohesive mm, resistance per u- unit length. So the total cohesion will be C into your length of the entire slip failure. Then you take the moment, calculate the driving and the resisting forces. You take the moment. You take the moment of your driving and your resisting forces. Resisting moment will be your Cu into r theta, which is the total cohesion along the slip surface multiplied by because this is a all the points on the line will be at a distance of r from the center. You have to multiply it by r divided by distributing moment, which is your weight of this wedge multiplied by the distance of the center of gravity of this weight with the uh, center of the slip surface. So remember that this type of analysis is usually performed to give stability of an embankment immediately after its construction. This is specific uh, type of problem this analysis is used in. This will not give us accurate results for every kind of analysis. So just after the embankment immediately is has been constructed, at this stage, it is assumed that the soil in the embankment has no time to drain. The strength parameter used in this analysis are ones representing the undrained strength of the soil, which are found either from UCC or the undrained triaxial test without pore pressure measurements. Okay, so we're not taking effective stresses, we're taking total stresses. Okay, that's why it's called the total stress analysis also. So, effect of in this method, we also study the effect of tension cracks. Tension crack basically, if you have a failure surface like this, it's not necessary that you will have a complete uh, circle uh, that we have idealized. Sometimes, especially when the cohesion is high, uh, cohesive soils tend to fail in a and they have a more vertical um, failure surface at here. So the failure surface here will be like this is the idealized failure surface, but actually some of the soil will stick to the main body, and you will get this vertical height up to a critical height, and this is the same height that we calculated in our lateral stress theory, the height up to which the cohesive soils can remain unretained and they can still remain stable. So this was kind of the earth pressure diagram of a this was the earth pressure diagram of a cohesive soil. So up till this height basically, because these are balancing each other out, up till this height you can have unretained. Yes, please. Is there a question? Okay. So up till this height you can have an unretained slope, and this basically is the same height, which is the HCR critical height here. Okay. So what happens in this is that, first of all, now how will the factor of safety change? First thing here now is that this weight will not excuse me, this length will now not participate in the resisting of the slide. Okay, so you have reduced this much of your resisting length. Now your new length of resistance for the failure is this. Okay, the second thing is that you don't, one second, just a moment. Okay, so next thing is, okay, the effect of tension crack is to shorten the arc if the crack is to be allowed for the subtended angle is to be reduced as shown in figure. Okay, so usually what we do is we can also decrease the weight of this wedge, because now it is not participating in the resistance here. Okay, but we usually uh, retain it because of the basically what happens is that there is some water that gets retained behind this tension crack, and to account for that we usually take the complete weight of the wedge. We don't decrease that, we only decrease the arc length. Okay, so this is the second type of method that I mentioned, that you divide the whole failure wedge into small slices, and then you apply limit equilibrium analysis on these wedges. Yes, yes, Arif.
Good evening, madam. Small question, madam, here.
Yes, please, yes, please.
This last three slides, what you are talking is about phi u is equal to zero analysis. Is it
This,
right,
na?
madam? Yeah.
Yeah,
No,
yeah,
no,
yeah, yeah.
not this, not this.
Yeah,
This,
yeah, yeah. This one, this
yeah,
one. Yes, yes.
this one is called for purely clays.
Yeah, this is the total stress analysis.
Yeah, this is for purely clays. Phi u is equal to zero analysis means this is for only we have C parameter. There is no any phi.
Phi u equals zero does not mean purely clays. Phi u zero is basically your total stress, just like it is written here. I'll show you. So you get your soil parameters from UCC or undrained triaxial test. So the undrained triaxial test will give you phi u is zero. You do not calculate the phi in that test.
Yes, madam. But what is the soil type actually? In the slope, what is the soil? Is it sea soil, C5 or 5 soil?
This is cohesive soil. This
Cohesive
can
soil.
be this
Mm-hmm.
can be C5 soil, but as I said that this is a very particular case in which we use this. First of all, because this is an embankment that is man-made. First of all, it is that kind of soil that is good for that we usually make in the use in the embankment, which is most of the times cohesive soil. Okay, basically what I mean to say is that this is a uh, we can say that it is a idiosyncrasy that we say that this is a sandy soil and this is a clayey soil. This is a purely phi soil. This is a purely C soil. Usually, that is not how we get the soil. This only what we write in the textbook. Okay. Usually the soil that we get, it's almost most certainly C5 soil. Sometimes the cohesive content will be cohesive strength will be greater than the phi strength, and sometimes the phi strength will be greater than the cohesive strength, but there always a mixture. Okay. So here what we are talking about is C5 soils basically.
Okay,
Okay,
madam.
soils
Okay.
with two components. But
Okay.
first of all, because this is the specific case, stability of embankment immediately after the construction, and it is assumed that soil in the embankment has no time to drain. We are not saying that the phi is zero, we are saying that phi u is zero.
Why I am asking is normally we don't use any pure clays for embankment construction.
Yeah,
That is why I'm asking.
that is what I am saying.
Yeah.
That you don't use you like it's a misnomer to say that the it's pure clay or it is
Okay.
pure sand.
Yeah.
This is a phi u is zero case.
Okay. Soil is a C5 soil, but it's a phi is equal to 0 case.
Phi u is zero case because you
Mm.
are taking the undrained shear strength,
Okay,
and
madam.
this is
Understood.
immediately after the construction.
Understood.
Okay.
Thank you.
Okay, so there will be okay, we're talking about slope stability. So in these cases, the center of the most critical circle can only be found by trial and error. Various, so as I said, what we want is we want the we want the radius of the slip circle, center of this slip circle, and we can find n number of factor of safety. So, like I mentioned here, for different radii, let me take just where's my pen? Okay, so I take on trial basis R1, R2, R3, R4. Okay, then I calculate the forces on these wedges, the moment of these forces basically. Then I calculate the factor of safety. No, no, sorry, this was not these were the wedges. Okay, so let's say for R1 I'm trying this. Okay, so I'll calculate the horizontal forces on the wedges. I'll calculate the vertical forces. I'll calculate the moment, and then I will calculate the factor of safety. Okay, I'll do this for R2, R3, R4, and then I can see that the configuration that gives me the minimum factor of safety will be your critical slip surface. Okay, so basically up now can you can think you can try to uh, the method is same. There are two different possibilities. So the main thing is same. I will take a radius. Let it here. I will take a radius. I will calculate. I will divide the wedge. Divide into wedges the failure plane. Calculate the horizontal vertical moments. Calculate factor of safety. Repeat for our different hours. Choose R minimum. Uh, FOS minimum as critical failure surface. But now the question arises how I will decide on how to take this R. Second question arises is what definition of factor of safety, uh, not the definition of factor of safety, uh, how the stresses will be analyzed. Okay, I'll share something. I'll share this 1 second. Excuse me. So what I mean, we can go through this paper. I don't want to scare anybody with these jargon and everything, but just so that you have a broad idea. Okay, so as I said that these methods are called limit equilibrium methods, in which we postulate that the slope might fail by a mass of soil sliding on a failure surface. At the moment of failure, the shear strength is fully mobilized all the way along the failure surface, and overall slope and each part of it are in static equilibrium. The shear strength is normally given by Mohr-Coulomb criteria. For total stress analysis, we take Cu, and for effective stress analysis, C dash is equivalent to sigma dash tan phi. So basically, what why I am showing you this is because I want to uh, show you that all of these methods stem from the same concept. They have the same basis. There is just slight tweaks in different methods that can make it method author A, author B. Okay, so all of these methods take factor of safety as shear strength available over shear strength required for stability. So infinite slope method, assumption about in interslice forces. So okay, so we'll come back to this so that I can this is the linear methods. Linear methods are simply the infinite slope analysis methods that we have been talking about. Okay, so this was the uh, 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 infinite slope method. Then we have a wedge analysis, phi u0 method. This is the simplest of the circular wedge analysis can be given here. Let's discuss this um, uh, later. Okay, phi u method, which we were discussing just now. This is the simplest of the circular arc methods for analysis. Failure is assumed to occur by rotation of a rigid block of soil on a cylindrical failure surface, along which the undrained shear strength of soil Cu is mobilized. Okay, so this is a cylindrical as in extending the in the plane direction. Uh, this is something that I mentioned about the plane strain stresses. This is the plane strain case, so it will be uh, uh, it will continue indefinitely in the direction normal to the paper or we have here cross section. In the early analysis, the shear strength was assumed to be constant along the failure surface. We used to take a constant failure surface, but with introduction of the fall cone test, other method determining strength. Mm, so this is what we were discussing with the total stress analysis, isn't it? Then we have the method of slices. The ordinary method of slices. First, we have the ordinary method of slices. In the phi u equals 0 analysis, undrained shear strength mobilized along the slip surface was assumed to be independent of the stress level. We simply say that unit length, the strength is Cu. For the complete failure surface, it will be Cu multiplied by the length of the failure surface. So we are taking it independent of the stress level. It does not matter how deep your radius or the failure surface is. If it's shallow, uh, there is no effect of the normal stresses, isn't it? But in this case, you see, in an effective stress analysis, here we were talking about total stress analysis. Now we'll talk about effective stress analysis. We'll apply the same principle to the effective stress analysis, to the using the effective stress analysis. So what is the difference here is that we will take the failure criteria as C dash plus sigma dash tan phi. Mobilized shear strength tau is S by F, where F is the factor of safety. Now P sigma L T, assume that resultant of the moment of equilibrium. So you divide all of this in wedges. You divide this into wedges, and you take the moment of the forces about O, and then you sum it to calculate. Just a moment. Calculate the factor of safety. So factor of safety is the summation of the resisting force along this failure surface over the driving force, driving moment, resisting moment and driving. This was the ordinary method, and we can even have a force polygon here. Then we have uh, mm, okay. Further, if you go beyond ordinary strength methods, we talk about Bishop's method, Spencer's method, Morgenstern Price method. Here we do not take the failure surface to be simply uh, as mentioned circular. Actually, this is the diagram where they have mentioned how we take the uh, trial for the radius, which is based on basically the friction cone method, friction circle method, sorry, and we can come to that later. But here, so if we talk about a generalized formulation of a irregular nonlinear uh, failure surface, let us say that I have a failure surface and then I divide it into wedges. What I am doing here practically is I am defining the equilibrium. This is the wedge, this is the weight of the wedge, this is the length of the failure surface corresponding to this wedge, and these are the interslice faces, and W is the weight, XL and XR are the vertical interslice faces. XL is the left interslice force, XR is the right interslice force. EL and ER are the horizontal interslice forces, where EL is the left horizontal interslice force, ER is the right horizontal interslice force, and let us say that this alpha is this angle is alpha for this slice. This angle can be different for different slices. If I go here, the angle will change, angle will change, angle will change. Okay, and B is the width of this slice. T is the total uh, stress, total tangential stress along this uh, failure surface. P is a resultant uh, um, of the forces, say T and W. Okay, so generally we make this body force diagram, and here if you see, in order to solve, you make you make these calculations for uh, force equilibrium. Okay, so the forces in the horizontal direction, the forces in the vertical direction, and the moments should be zero. Okay, so you take the uh, overall moment equilibrium, and you take overall force equilibrium, and you get these equations: F, factor of safety based on the moment equilibrium, factor of safety based on the force equilibrium. Okay, and in order to solve these, you take some assumptions for the interslice forces. Okay, so it is as simple as that. There is a slice, there is a body, you draw the free body diagram, you take the moment equilibrium, you take the force equilibrium. Then these are the forces acting on the body. If your assumption is that your interslice vertical forces are in equilibrium such that xr is equal to xl, then, like, Bishop proposed this assumption to solve for this whole problem. If you take Spencer's method, Spencer has given the theory in which he has taken the interslice forces and interslice vertical and horizontal forces to be constant, the ratio. And Morgenstern Price is a modified version of your Spencer's method. Basically, all of these methods are doing the same thing, they're just giving a different assumption for the solution. Okay, so this is the Bishop's method in which, okay, so that is about the factor of safety. This is your Spencer's method in which you x by E is taken as tan theta, and then you have Morgenstern's price method. We were talking about how we take the radius. Okay, we can talk about that. Okay, so this is let's discuss this procedure. Suitable procedure is suggested in the figure below. Center of each trial circle is plotted, and F value of the circle is written alongside it. After several points have thus been established, it is possible to draw contours of F values which are roughly elliptical, so that the center indicates where the center of the critical circle will be. Note that the value of F is more sensitive to horizontal movements of this circle center than vertical movements. So you take different points on this. Here you take different points on trial and error basis, and you write, you calculate the factor of safety and write the value. As you write the value, you can actually see contours forming, contours of same FOS forming. Maybe I'll have 1.3, 1.4, 1.5. So as you see these contours forming, you can get to uh, assume the center of these contours and then calculate the critical angle at that center. Okay. The method proposed by Fellinius for locating the center of rotation for cohesive soils. So Fellinius has given a beta, they have given an alpha. You take H and you take H here and you draw this, and then this method is self-explanatory in the notes. So let's not, okay, briefly fill. Okay. I think that is enough theory about the slope stability failures. Slope stability. We can do the question on the retaining wall so that in next class we can do some questions on the slope failure, because otherwise we will run out of time. Okay, is that fine? Okay. Can we take a 2 minute break? Just- Okay, shall we start?
Yes, madam.
Okay. Okay. Determine the active force after tensile crack occurs and the passive force. So we have been given a rotating wall, and like we were discussing about tension cracks earlier, usually these uh, tension cracks take place in cohesive soils because they have a tendency to stick. Okay, so phi has been given as 26 degrees. We can calculate Ka 1 minus sine phi over 1 plus sine phi. This comes out to be 0.39. We can calculate Kp 1 by Ka, which comes out to be 2.56. Okay, so basically in this problem, you have a surcharge loading, surcharge loading in itself will be constant, and then you have a basically, you know, for C5 soils, sigma is equivalent to C plus, sorry, tau is equivalent to C plus sigma dash tan phi. And if you use the sigma 1 and sigma 3 notations for tau and sigma, you will see tau is, uh, how do you write tau in principal stresses, Arav?
Madam,
How do you write tau in principal stress forms? Sigma 1
tau is
minus,
a deviatric stress. No?
I know, but you
Yeah,
write
by
it
2. That's correct only. Whatever. Sigma 1 minus sigma into sine to alpha.
sine 2 phi.
Yeah. 2 alpha,
And
madam, not phi. Yeah, 2 theta, okay. It's okay.
then you have sigma n equals sigma 1 plus sigma 3
By
by
2.
2 plus minus square root or not. I don't remember. Cos 2 theta
No, no, no. Plus continue, madam. Plus
plus
sigma 1 minus sigma 3 by 2 cos 2 theta.
cos 2
Cos
theta.
2 theta.
Okay. And you have theta is equivalent to 45 plus minus 5 by 2. Isn't it? So
Why you want, madam, all these?
I am writing. I basically wanted to I was discussing the presence of
Ac- Activate
norm.
pressure.
Yeah, I was
Activate
discuss.
pressure equation, you can write, madam,
Yeah,
directly.
I can write. I was just discussing why
Mhm.
we have a negative uh, uh uh, this thing here.
Okay.
Okay, that is fine. If I'll continue with the equation only then.
Yeah.
Sigma A equals Ka sigma naught dash 2c dash root Kc. Sorry, Ka. So at z equals 0, you have overburden equals 0 and your sigma A is minus 2c dash root Ka. So let's write this.
Surcharge term is Ka into Q, madam.
Yeah, times 8 times of 0 point. Okay,
Yes, madam.
here we will have what will be this
10.11.
huh?
10.11, madam.
Okay.
Negative value is 10.11. Surcharge value is 4.
So this will be
Net value 6.11. Negative.
15 0.4. Okay, just have to add these now.
Yes, madam.
The height will be You know,
Madam, the net diagram, after
hmm,
knowing the final answers, we can try it, no? Negative or positive based upon that.
hmm,
The net diagram for these two,
hmm,
first we calculate the top value and bottom value, net answer, and then we accordingly we can draw the diagram.
yeah, yeah.
For example, now the net answer on the top is minus 10.11,
This will be minus 6.11.
6.11, negative.
Yeah, minus 6.11.
11.
What will be the height here?
That we can calculate in the net diagram, madam. Why you want to calculate for independently? We don't know whether we get or not, no.
Okay,
So
so
we can go at the bottom. Ka is zero point 0.4 into gamma is 15 into height is 4 minus 10.11. Hmm. This value plus 4. Bottom value 17.89. Net
you
answer,
have to
madam. Net answer.
net, na?
Net
This
is a,
one?
yes, madam. No, not that. In the right hand diagram, new diagram.
Yeah, yeah. This one was 17 point.
No, madam. If you add a
Calculate.
surcharge also, then it is 17.89. Surcharge is same, no? It is a 4. Top and bottom, surcharge is same.
Yeah, yeah. You calculate this of this triangle. Calculate the base and this.
1 second, madam. 0.39 Ka, gamma is 15, into height is a 4, minus 2C Ka gamma is a 10.11. This is 13.29, madam, what you are asking now.
13.29.
Uh, Positive.
Okay.
And surcharge is a 4, positive.
Surcharge is 4. Yeah.
Yeah, bottom surcharge. Top and bottom same, no? It is a
Yeah.
4.
Yeah. I written plus here.
Yeah.
Okay. So then we have. Oh,
A net answer of 17.29. And we can join these two.
yeah.
Now we can take a similar triangles and you can find out formula. I don't think it is possible now.
Okay.
You can assume from the top x value, negative diagram.
Just a
And
moment.
yeah,
Just a moment.
yeah, madam. That is, we can assume x. That's correct only, na, madam. Why you are erasing?
Yeah. Just a moment. Here. And uh, we have increased this. Something like this.
Yeah, madam. Bottom adding, top is reducing.
Yeah. This will be the
Yes.
new diagram. This will be 17.29. This will be 6.1
6.11.
minus
Yes, madam.
minus 6.1. And then we will have a reduced height. Let's see. Okay. Active uh, force PA after the tensile crack occurs. So this was okay. The tensile crack has occurred. We need the PA. Okay. Just a minute. At this point, your sigma active will be 0. This will be completely balanced. So your Ka times sigma naught dash minus 2c root Ka will be 0, or your Ka times sigma naught will be 2c root Ka, or your sigma naught is q plus gamma hc equals 2c root Ka over Ka. So gamma hc equals 2c by root Ka minus q. Hc is 2c by root Ka minus q over gamma. Okay, can you calculate this?
I have done directly by similar triangle, madam. By
Yeah.
assuming the x value,
Mm-hmm.
I got 1.044 tensile crack.
Okay.
1.044.
This is the same that I'm getting from the formula. Okay.
What you have written just now, madam?
Yeah.
Can I check that also?
Yeah, yeah, you can check. Like you want to calculate this?
Yeah, if you want, I can do it.
Yeah.
Otherwise, no.
Yes, yes, you can calculate. I get
One
the same
second.
answer. You can calculate.
Yeah, 1 second, madam.
Minus second.
Almost same, madam.
Yeah. Okay. So we have been given H. So your PA will be simply half of base into altitude. Okay. After the tension crack, your top wash portion will not act in active uh, pressure. So your PA will be 25 point kilonewton per meter. Okay.
Yes, madam.
So we also have to calculate the passive force. So for the passive force, again we will have passive force will be, see, Kp was 2.56 and your K naught plus 2C Ka. Kp. So you already have Q here, 0.10, and then you have 2C root Kp here.
No, it is not 4, madam. Kp into, no, it is not Ka you have taken by mistake. Kp
Here.
into Q.
Okay, okay.
Ah, Kp is a 2 point,
25.6.
yeah.
Okay.
It is going to be 25.6, yeah.
This will be Ka sigma naught. Basically, this will be, can you calculate the base length?
179 point total value, bottom.
Hmm.
179.46.
And
Top
here,
is a 25.6. Left hand diagram no need, madam, because already you have included both.
yeah,
Left hand side diagram you can erase, madam,
okay.
because you
But
have already written trapezium, no?
yeah,
Rectangle plus triangle.
but this I have written only 2C root Kp.
Yeah, that value only I told 25.6 on the top.
But then here you will also have na
No need, madam. That
Kp
entire
into.
diagram you can remove.
I
2C
understand.
KP.
Uh,
Uh-huh. Yeah, madam.
no,
You can
you,
remove that.
yeah. I will. I'm actually trying to draw it in parts.
If you draw the separately rectangle, then another diagram should be only triangle, madam.
Isn't doesn't your passive pressure have a 2C Kp here, a root
Yeah,
Kp, and then it has a triangular part?
that is a net diagram, madam.
That is fine.
But,
This is a additional Q, na?
madam, you have written plus symbol here.
Yeah.
That means left hand side of the plus symbol, that is because of 2c square root of kp.
No, I'm writing here only
Uh,
because of Q. This Q.
okay, then in that case, right hand side, no, you should not include the q, no?
Where I
Only in right hand side, you should get only triangle. That is a kp into sigma naught diagram. Rectangle plus triangle is equivalent to trapezium. No?
yeah, 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 yeah. Just a moment. Just a moment.
Yeah,
I'm
that is
getting
what I'm
confused.
asking.
Just a moment.
Madam,
Yes.
you want to draw separate diagrams and you want to add, otherwise you want to draw the net diagram, madam.
Uh, say, what is your sigma p? Isn't it
Yeah,
kp
Kp into
sigma
Q.
naught plus 2c root kp?
Additionally, Kp into Q also is there. Plus,
No, forget
because such
this.
as you have given, madam.
You forget
Ah,
this for now.
okay, okay. If you forget that, then this formula is correct.
Isn't this?
Yes, madam. Correct, madam.
When
If you
your z is 0,
then it is okay,
your
madam. Then in
sigma
that
naught
case,
is 0,
hmm,
then your sigma p is 2c
2c
root
square root of
kp.
Kp. Yeah.
That is what I was drawing here, na? You're confusing me, man. That is what I'm drawing here. I'm writing this as 2c root of kp. I'm writing this
Okay.
as q into.
Such as you are separating.
Yes, that is what I have done here also.
Okay, okay, okay. Okay, madam. I thought of
Haven't.
vector diagram also trapezium.
No. This is because of q. I've written here this is because of q. And
Hmm.
then this is your passive earth pressure diagram. Your sigma p is given by this. At z equals 0, your sigma p is equivalent to 2c root kp. And that is what I have. What is 2c root kp? Can you calculate?
Yes, madam. One second. 2 into 8 into square root of 2.564. 25.61.
So your this will be when you add them. That is why I had drawn two panels because I was separately calculating it. This will be 25.56. Add them, this will be 51.2.
1 second,
Okay.
madam. One
Yes,
second,
please.
madam.
Yes, please.
Is equal to. Fine, madam. Yeah.
And then you have this is 2.56 into 15 into 4. This is 179 plus
Around
51,
20.
204.8.
Yes, madam.
Then you calculate the area of this trapezium. PP will be 51.2 plus
5.
104.8 into 512,
Point four.
708. Okay,
Yes, madam.
yeah. We can calculate the x bar, which will be based on these separate. You can take the moment at the base, moment of this rectangular at the base, and we can do that 51.2 into 4 into 2 plus half of 179.46 by 3 divided by 500. So give you point. Okay.
Okay, ma'am.
There are two more questions that I wanted to discuss, but the time is already up. So I will just briefly mention what we have to do in these questions. In this question, basically what you do is you calculate the depth of the critical. Uh, for example, you have an earth pressure diagram like this. You calculate the critical height for the clay. For example, if it's here, then you just ignore the uh, contribution of the tensile part. Okay, but first you have to calculate HC and then you ignore the contribution of the active part. Okay, then
Okay.
in the next question, we have to determine the active lateral force and its location. Basically, this is simply your Coulomb's theory. There is a long formula that has been given for your walls that are inclined, that have an inclined back. The walls have a rough surface. The surcharge, the backfill has a surcharge. The backfill is inclined. So all of the different uh, cases have been incorporated in here, and you just have let me just give this here. KACS cos square phi dash minus eta over cos square eta cos of eta plus delta 1 plus sine of phi plus delta sine of phi minus beta over cos of eta plus delta cos of eta minus beta 1 by 2 square, where your angles are given like the batter of the wall is eta, the incline of the backfill is beta, and your friction angle norm the angle between the resultant and the normal is delta. Okay, and in this case eta is 0, beta is 8, delta is 15, and 5 is 25. You can calculate the value of KAC, and after that you simply uh, draw the active pressure diagram. Like this. Okay. Yeah. So I think that is time for today. Let's uh, meet you in the next class. Thank you very
Thank you,
much.
madam. Good
Thank you.
night, madam.
Good night.